Hi everyone, I am Shuping from School of Material Science and Engineering at Jiangsu University. Thanks for giving me this opportunity to introduce my work. Now, today, my topic is sustainable nanofiber membrane for water treatment. First of all, we look at my research background. Water pollution, as our guys know, heavy met heavy matter pollution is one of the most serious uh, environment issues. As you know, the density heavy matter is more than 5 kilometer per centimeter square. The number about is are 45 species. Now, the total industry wastewater discharge in China is 19.75 billion tons, accounting for 24.1% of the total national wastewater discharge. So, heavy matter have some toxic characteristics such as non-biodegradable, biomagnification through food chain, trace concentrations such as toxic through the food chain. High toxic can cross the blood-brain barrier. Uh, there are five toxic matter, heavy metals such as lead, cadmium, chromium, arsenic, and mercury are listed as strong carcinogens by the International Agency for Research on Cancer. So, heavy metal pollution or other or organic pollution has led to scarcity. Water scarcity now has emerged as the major constraint on global economic growth and sustainable development. There are two-thirds of the world face severe water shortage. About 4 million people uh, face severe water shortage during at the last 1 month every year. More serious, every year, millions of people die from disease caused by drink contaminated water. Now, there are numbers are expected to increase, exacerbated by climate change and the population growth. So, it's essential to develop a cost-effective, robust, and sustainable method for water purification. Now, the con- the convention the convention water treatment method, including that ion exchange, absorption, sorry, uh, coagulation, electrochemical technology. There are this convention method often need high cost and complex pre-treatment. Now, the membrane technology are using water treatment separate contaminants from water based on properties such as size and charge. They have attractive uh, properties, so it is made becomes the mainstream for water treatment. Uh, membrane separation is has is become a popular water treatment technology with high efficiency, energy and save and high efficiency, energy saving, and good effluent qualities. There are many techniques for fabricating water purification materials. One of them, electrospin, is a fast 5 nanofiber production method that this technique uses electroforce to draw charge shred a polymer solution and the polymer made up to fiber diameter in the order some hundreds nanometers. The advantage of the electron spin include a wide choice of materials, high controllability of the structure, easy of adding functional components to nanofiber, and high porosity and uniform pore size distributions. So in our work, we may use the electric spin method to construct the nanomaterials. Uh, Compare with that the artificial polymers that the sustainable materials have some attract attention in in the fabrication of advanced materials. Typical protection strategy of sustainable material from renewable biomass feedstock for water treatment exasperate about the figures that biomass materials are made from renewable biology resource such as agriculture residues, uh, mm, shrimp, shrimp, corn cobs, wheat straws, and crab shells. Uh, some animals and bacterial fusions. The main components of sustainable materials are natural polymers, including cellulose, hemicellulose, lignin, starch, protein, and chitin. One of them, ketosane, is the may protect the anti-oxidation of chitin, which is the most basic and important derivative of chitin. They are widely accepted in share of crustaceans, shrimps, crabs, insects, as well as the several fusion organisms, such as we can see that there are uh, many crab, many species contain that the catechon. Uh, so The catechin have a remarkable structure that the molecule of catechin has amino groups and hydrogen groups. This group have benefited to animate charged contaminants from wastewater and have a strong ability to form nano complex with a variety of heavy metal ions. So, these features make the catechins highly attractive for use as absorbents and water filtrate materials. Uh, my first, our first introduced to or introduced the work is the catechin PVP PV electron nanomembrane. In our work, a lower electron cytosine PVP PVA nanofibrous membrane was prepared to remove heavy metals and organic pollutants from water. The morphology and structure of this kind of nanofiber membrane are systematically investigated, and meanwhile, the separation and the absorption property of nanofiber membrane were tested with a variety of target pollutants. Furthermore, um, we investigate the filtration absorption mechanism and filtration and and test and determine the water flags of the nanofiber membranes. Okay, this is the CS, PVP, PVA nanofiber membranes morphology. From this graph figures, we can see that the nanofiber with uh, the fiber diameter is increased is decreased with the different with the increase of CV PVP concentrations. Now we through the control of the component concentration, we could be obtained at the well distributed bit-free, smooth, and continuous nanofiber that at the PVA solution concentration about 60 to 80 weight%. The diameter of the nanofiber on the optimized condition are mainly distributed between 50 and 30 nanometers, and with an average diameter is 160 nanometers. Now we can see that the different solvent, the morphology is significantly different at when the solvent is made a acetic acid is 90% weight. 90% weight%. It is true that is smooth and uniform fiber size. Through the BT absorption and desorption isomer and the precise description, we can obtain that the following the information that the pore size of the nanofiber was distributed between 1.74 and 3.17 nanometers. The distribution was more contributed at 2.3937 nanometers. The membrane flex and the separate performance was show that the nanofiber membrane permission flex for pure water reached 1,518 18 meters square per hour per bar. The rejection for copper, nitro, and other pollutants are highly high projections. Okay. On the basis of the first nanofiber, we also can construct the CS, PVP, PVP, and the CNT electrospinning nanofibers. The following figure shows that the schematic diagram of this kind of this dual nanofiber membranes. First, we use that the first our first work create nanofiber membrane as substrate, and then we incorporate the carbon nanotube into CSPVP matrix via electrospinning to constructing the nanochannel. This nanochannel could create good permissionality. From the SEM, we can see that this dual this bilayer have a good nanofibers that the size of this nanofiber have approximately 180 nanometers, and the diameter from the diameter range from 50 to 400 nanometers. Okay. Left hand shows the figure shows that our can construct the nanofibers for photo. From this photo, we can see the membrane have a good could be exhibit high flexibility and can be twisted without damage. The up figures shows that the synthesized membrane had a thickness of 8 millimeters. The red hand down the figures shows that the active layers was tightly integrated with the electron substrate. This figure shows the morphology and the cross-section image of the CSPVPCNT active layer as function of electrospray time. As with the increase of electrospray time, the thickness of the thickness of active layer also increase from 15 minutes to 60 minutes. The thickness increase from 5 millimeter to 26 millimeter. From the FAM image, we can calculate the rule mean square roughness and average roughness. The maxi roughness of this membrane coated active layers RQ equals 227 nanometers. RA equals 176.97 nanometers. Okay, this result we illustrate that we could control the expiry time and we'll find adjust the membrane thickness. We also conduct the thermogravity analysis for the nanofilm and this bilayer membranes from this we could see that this membrane have a good thermostability, and also from the contact angle on the thin film composite membrane, that water contact angle of the membrane increased from 10.8 to 22.2 with the increase in spray time, indicate that the hydrophilicity was negative correlate with electrospray time. The change of water contact angle may be attributed to the inherent features of the carbon nanotube and the more complex micro nanostructures. We also can perform the performed in the membrane separation formation. This figure shows that the membrane's separation performance. Also, we get that the relationship between flex and the electrospray time, owing to the thin and porous structure of selective layer, the pure water permit flex of the TFC membrane reach up to 225 liter per millimeter per square and per hour, compared to commercial PVDF ultrafiltration membrane. The improvement was 32 around 32% and 33%, 40%, and 35% respectively. The high rejection and indicate that the result in TFC membrane has a broad application prospect in the field of water purification for micro pollutants removal. Okay, we in this two work, we can obtain the following conclusion. CSPVP, PVA nanofiber membrane were synthesized for the adsorption and filtration of heavy metal ions and organic ions in water by electric technique. CSPVP PVA nanofiber membrane form a uniform distribution pore structure at 118 nanometers. Meanwhile, the nanofiber membrane experience good separation performance with purer water permeate. On the other hand, on the base of the first construct the fiber, we construct the high flex bilayer nanofiber membranes by electrospin and the electrospring technique for highly efficient heavy matter and organic pollutant removal. More importantly, the introduction of carbon nanotube inactive layer provides additional nanochannels and improve heavy matter and dye separate performance. Under optimized condition, we get the remarkable water permeable flex and the high rejection of organic pollutants and heavy metal ions. Meanwhile, this resultant membranes also exhibited a long-term stability and a good antifoaming property. Overall, this strategy may pave a way to the fraction of advanced sustainable materials for potential application in water purification. Okay, that's all. Thanks for listening. Bye bye.